We are now considering the motion of a rigid body, and we'd like to talk about kinetic energy of rotation and properties of that rigid body. Let's consider a rigid body, and let's say that our rigid body is rotating about an axis passing through a point S. If we look overhead at our rigid body, then what we're going to do is introduce a coordinate system. So this is our overhead view. And suppose that we have a small element of our rigid body here, which I'm going to write as delta mj, and that's a distance rj from the center. Our rigid body has an angle theta, and what we'd like to do is describe a coordinate system r hat, theta hat, and k hat, pointing like that. Now, with this rigid body that's rotating, we describe the angular velocity as the rate that the angle is changing with respect to k hat. And so we can draw the vector omega, and this establishes our coordinate system for our rigid body and a small element of mass delta mj. Now, what we'd like to consider is, what does this mass element do? Imagine that it's over there. Because every point in the rigid body has the same angular velocity, this object is going in a circle with angular velocity omega. Recall that omega is perpendicular to the plane of motion, but the object itself has a velocity, which I'm going to write vj, and that velocity vector, vj, is in the tangential direction, and it's related to the z component of our angular velocity by the following relationship. It's how far we are from the center point, S, times the z component of the angular velocity, and it's pointing in the tangential direction. So remember that omega z is equal to d theta dt. And this describes our coordinate system for the rigid body. Now what we'd like to discuss is the kinetic energy. And the way we're going to consider kinetic energy is we're going to sum up the rotational kinetic energy of every single mass element. So we begin by writing kj rotational, and we know that that is just 1/2 times the mass element times the velocity of that element squared. Now we can use our relationship for the tangential velocity element related to the angular velocity, and we have 1/2 delta mj rj squared times omega z squared. Now keep in mind that omega z is the same for every single mass element, but the distance the mass element are all different by rj. So the total rotational kinetic energy is the sum over j from 1 to n of, let's put the half outside, times delta mj rj squared. Now again, recall that every element has the same omega z, so I can write parentheses omega z squared. And that's our rotational kinetic energy. Now what we want to do now is look at the limit as our delta mj becomes very small because we have a continuous body, and we'll write a definition which is going to be the moment of inertia passing through this point S about the axis passing through S is equal to the limit as delta mj goes to 0 or n goes to infinity of this sum delta mj rj squared. J goes from 1 to n. Now, because this is a limit for the continuous body, we'll define it as the integral over the body of a small mass element dm that's a distance r squared. Now here, what is the meaning of the r? Well, for our continuous body here, if we call this dm, and we define the distance from S to the body r, and now I'm going to just put a little notation in here. It's the distance from S, the axis we're calculating about, to where the body is dm, so I'll write S dm. And this is what we call the moment of inertia of a continuous body. Now, again, what's very important to realize, it's a moment about a particular axis. So this is about an axis passing perpendicular to the plane of rotation and through S, the point S. So it's an axis that's passing perpendicular to the plane of rotation, passing through the point S. And this is what we call the moment of inertia of a body. Now we'll see that the moment can be expressed in terms of our other physical quantities. As the course develops, you'll see 2 or 3 more fundamental relations for moment of inertia. But what we'd like to do now is summarize our results, that the kinetic energy of rotation is 1/2 for rotation about this axis. I'm just going to indicate passing through S of IS times omega z squared. Now, keep in mind, because omega z is a component, it can be positive, 0, or negative, but the square is always a positive definite quantity, and that's our kinetic energy of rotation. Let's contrast that with our translational kinetic energy, and we remember there that was 1/2 times the total mass of the object times v squared cm, where we're looking at all of the object at the center of mass, and this is the total mass of the object.